Shown here are two common reactions found in very common metabolic pathways. The top one is found in the glycolytic pathway, whereas the bottom one is found in the citric acid cycle. Now, the context of those biologically is very important. However, I would rather focus in this recording on the free energy changes that are reported next to the reactions. Specifically, what you see here is this, that in each reaction, the standard free energy change that I just underlined is different than the actual free energy change. And the question that we want to address is, why is that the case? And how can we use these two numbers to understand and better understand the reactions both at standard conditions and at actual conditions? An analogy I like to use when we start to consider the difference between standard free energy and actual free energy is that of a hiker. So if you were going on a hike, one of the things that we often measure on a hike is our elevation gain. Let's say that you're going to climb one of the mini 14ers found in Colorado. And you want to know, well, what is my elevation gain going to be for my hike at its highest point? Presumably the summit of your 14er. Now you could say that my elevation gain is 14,000 feet. However, that would be rare. And the reason is because rarely do we begin a hike to climb a 14er, especially in Colorado, at sea level. Now, the elevation of the 14er is truly 14,000 feet above sea level being our reference point. And if you were to start at sea level, your hike, then we would have an elevation gain of 14,000 feet. However, we typically do not start a hike at sea level. We typically started at some other elevation, let's say 8,000 feet. In that case, because we're starting at 8,000 feet, then our elevation gain is only going to be 6,000 feet at our highest point in the hike. So we have then two different potential elevation gains for our hike depending on our starting point. Well, that's similar to chemical reactions. They both are going to have the same ending point. When we look at, not these two reactions will have the same ending point, but when we look at a reaction, it will always have the same ending point. But the standard free energy change and the actual free energy change will be different because of where we are beginning that reaction. So let's first of all think about the ending point of either one of these reactions. And we can say this and generalize this to any other reaction. We can say that the ending point of a reaction will be at KEQ. And KEQ, as hopefully you remember, is going to be the equilibrium constant. So what we could add to this sentence would be, or equilibrium. When equilibrium has been established, then we can say that the reaction has come to its ending point. Right now, KEQ, real quickly, just to remind you, is the concentration of products over the concentration of reactants, meaning that it is a product-reactant ratio that is very specific for a particular reaction, right? So each of these reactions, the top and the bottom, are going to have different KEQs, and therefore they'll have different ending points, right? But when we look at the standard free energy change and the actual free energy change for them, and we measure those, the ending point for both of those measurements is going to be the same. Going back to our hike, the ending point of our hike would be the summit of the 14er. Now, to get elevation gain, that measurement would depend on where we started, right? So let's think about now the starting point for our reaction. And again, we can generalize this as we move on. And we can say this, that the starting point for a reaction under standard conditions will be a product to reactant ratio equal to 1/1 or 1:1, meaning that standard conditions will always begin at the same place. So any reaction that we place under standard condition will always begin at a product to reactant ratio where they're equal to each other, or 1:1. Okay, this would be the idea even of elevation. We always measure elevation from a reference point, and that reference point will always be from sea level. Well, we measure standard free energy changes from a reference point, and that reference point is 1:1. Now, let's go on and let's talk about actual conditions. Starting point for a reaction under actual conditions will be Q, which is also equal to a concentration of products or reactants. Okay? But that Q value, right, is essentially going to be the product to reactant ratio at some actual condition. For a biochemist, we would typically be concerned with a product to reactant ratio that we would find within, let's say, a cell, the cytosol of the cell, or the mitochondria. So if we were to look at this first reaction here, that is a reaction that should take place in the cytosol of a cell. And so we would say that the actual conditions are going to be the concentrations of fructose 6-phosphate, which is F6P, ATP, F16BP, or fructose 1,6-bisphosphate, and ADP that are actually found in the cell. And we could say the same thing for the bottom reaction, where the starting point and under actual conditions would be the conditions found in the mitochondria, because the citric acid cycle takes place in the matrix of the mitochondria. So we want to know the concentration of malate, NAD+, OAA is oxaloacetate, and NADH found in the mitochondria, and then we could calculate our Q value. And our Q value would be our starting point. So when we look at the difference between standard free energy changes and actual free energy changes, they are different because of where they begin. They will both, when measured, will end at the same place, and that's KEQ, but they have different beginning points. Now, to illustrate this point, a very helpful graph that can be used is a free energy landscape. And free energy landscape is going to be set up something like this, where we have on our x-axis, which is not labeled yet, but we can label it right now, we have free energy. G, not change in G, but we have free energy on our, I'm sorry, I said x-axis, but I meant y-axis. We have free energy. Now, on the x-axis, which is labeled, we have essentially the product to reactant ratios, right? Where when we are all the way to the left of our graph, over here, we would say that we are almost entirely reactants. All the way to the right of our graph, we would have something that would be almost entirely product. Right? And every point in between these 2 points that I'll put dots on would be some Q value or some product to reactant ratio, and we'll give some bearing for the x-axis by just saying our 1:1 point, where product and reaction ratios are equal, is going to be sitting right in the middle, right? And we could say the same, of course, for our axes over on the other graph. In this case, though, because our reaction is different, we would say that our reactants are malate and NAD+, and our products are oxoacetate and NADH. Now, what we want to do is we want to take these two values here, and we want to be able to plot out a free energy diagram or a free energy landscape using the values for both of our reactions, delta G prime naught, or our standard conditions, and our actual conditions, delta G, for both reactions. Now, here's what I'm going to encourage you to do. I want you to pause it, and I want you to go ahead and try and produce these graphs based off of this information found right here for both of these reactions. Now, seriously, pause it, because this is a good opportunity for you to practice this and how you do this. And then after you have your graph, come back and listen to how to make these. Okay, so hopefully you are now back and you have a graph that looks like, or that is your prediction of what this graph should look like. And so let's go ahead and do this. And so I'm going to put our values here for this reaction. It's delta G prime naught equals negative 14 kilojoules per mole. And delta G is equal to negative 22 kilojoules per mole. So how do I start to make this graph? And the first thing that I would encourage you to do is to try and determine the quote-unquote ending point of our reaction. In other words, the KEQ. And we can do that using this value. Right? If we were to look at this equation, it would equal negative RT natural log KEQ, which means that we could solve this equation for a KEQ and using delta G equal negative 14 kilojoules per mole, and therefore determine our ending point. Now, the arithmetic I think that you could probably do, but something that I will point out to you is this. And that is that when we look at this reaction, and it's delta G at standard conditions, we notice that it has a negative value. And because it has a negative value, then we can say that this is a reaction that is exergonic or spontaneous and will produce products to reach equilibrium from its starting point. Right? So in this case, we would say that the starting point, because we're at standard conditions, will be our 1-to-1 point. This reaction then will produce products to reach equilibrium, and therefore we're going to go in this direction to find our KEQ. Now the number 14 would tell us how far to the right we would go if we were to put a more precise gradation on our x-axis. For now, we'll just say that it's somewhere around here. And we will say that that is then the KEQ. A product-to-reactant ratio, because that's what we're plotting on the x-axis, at that particular reaction's equilibrium point. Now, I'm going to go ahead and then draw how free energy will change as a function of the Q value, or the product-to-reactant ratio. And what we will see here is this. It will go something like this. Right? Where at our equilibrium point here, KEQ, we're at the lowest free energy. So one of the things that we need to think about with the ending point of a chemical reaction being equilibrium, we can also say that that's the point where free energy has been minimized. Now, free energy is the portion of the total energy of the system that can do work. When a reaction reaches equilibrium, it can no longer do work, and we say that its free energy value has been minimized. At any other point along the free energy landscape, or any other point other than the KEQ, we have a free energy value that sits above that of KEQ. And therefore, the reaction is going to drop to that lower energy level, and it's going to adjust its product reactant ratio in order to obtain that lower free energy value. Right? Now, let's think about this in regards to standard free energy changes. We know that because we're at standard conditions, that the reaction under standard conditions will actually begin right where I just drew the dot. It's going to start there. And it's going to then proceed in the downward direction from an energy standpoint until it finally reaches that point, right? And that will be an exergonic reaction. And presumably the potential energy that the reaction has at our starting point, the 1-to-1 ratio, then is going to be a energy of 14 kilojoules per mole. And it can then drop down to that lower level, and it can do that kind of work. Now let's go over here and let's think about this reaction, because this reaction has very different standard free energy change. And then we'll put delta G is equal to 0 kilojoules per mole. So let's look at this one. Now again, this is going to be equal to negative RT natural log Q, so KEQ, sorry, not Q, but KEQ. So we could then solve this problem for, of course, KEQ and get a quantitative value of what it is. However, once again, we can do this. We can simply look at this and say, okay, there is a positive value here. There's no negative sign. And that means that then this is a reaction that is endergonic and non-spontaneous, meaning that to reach equilibrium, it will go in the opposite direction of the way that we've written it. It will produce reactants rather than products. So we will once again say that the reaction, because it's at standard conditions, will start at our 1-to-1 point, and it's going to produce its reactants to reach equilibrium. It's going to go in this direction. And I'm going to go quite a bit towards the left on this one, more than I would do so on my last example, because my number 29 is larger than my number 14, and so we would get closer and closer to the end of this axis. Right? So we could say that then this would be the KEQ for this reaction. And there would be a lot of reactant at this reaction's equilibrium and not very much product at this reaction's equilibrium. Now, once again, we can draw then our landscape, and our landscape would look something like this. Again, the lowest point here on our landscape would be that KEQ, because that's the ending point and where free energy has been minimized. Now, let's return back here, and we can finish this out, and we can then use this graph to illustrate what I've been talking about here in regards to the difference between standard and actual free energy change. The main difference between standard and actual free energy change is not where they end, but rather where they begin. Much like how we would measure elevation gain on a hike, that depends entirely on where we begin our hike. If we're saying that we're going to do, right, have the same ending point, right, a 14er. And so in this case then, we can look at this value here. And we have to come up to some Q value for this. Okay, now, once again, we could do this quantitatively. This would be equal to delta G prime naught plus RT natural log Q. That's what this equation would equal. We can then solve this equation for Q and come up with a value for it. However, once again, we can just look at this and we can say, okay, this reaction is going to be exergonic. It has a negative free energy change, which means that wherever we put our Q value, our starting point on this graph, it's going to have to be to the left of KEQ, right? Because it's going to have to produce products to reach equilibrium, which means that we have to have Q somewhere on the left-hand side of our graph so that it can go in this direction towards product to reach equilibrium. Now here's where these numbers can be really helpful when we look at them relative to each other. 22 and 14. 22, of course, is a larger number than 14, which means that this reaction under its actual conditions is more exergonic than it is under standard conditions, which means that it's further from equilibrium at its starting point than it is than it would be at under actual conditions, further from equilibrium at that starting point than it is for standard conditions. Right? So let's think about this. We are starting, as we have said, our starting conditions for actual conditions is right here, the 1-to-1. When we then look at the 22 value, we would say that then that Q value would have to be somewhere in this quadrant of the graph. So we could say it would be somewhere like here. And what that would indicate is that at that starting point, notice we're way up here now, that's where I'm looking, we are at a much higher free energy and we are further from equilibrium. Right? And if you think about this again as potential energy, the potential energy of our reaction at actual conditions, where that pink arrow is much greater than our potential energy at standard conditions, where we see that. And if you think about this like a skier, right, on the side of a hill, we can of course see that the skier up here in our actual conditions has more potential energy than of course the skier in the middle of the hill. Okay, and is going to have more energy gained if it were to ski, that skier were to ski down the hill. And so then of course this reaction is going to go funnel into that lower energy point, and the free energy change then is going to be negative 22 kilojoules per mole. Right, now, from a cellular standpoint, what that means is that this reaction is crowded over here by its reactants, and there's a lot of fructose 6-phosphate and ATP relative to its breakdown products, fructose 1,6-bisphosphate and ADP. In particular, ATP. There's a lot of ATP in a cell. The cell works very hard to maintain a high level of ATP. Now, we could say this. Let me just do this. This would be completely and 100% hypothetical, but let's do this. And again, I'll ask you to pause it. But what if I were to say that actual conditions were this? Negative 10 kilojoules per mole. Where would I put my starting value for this reaction, given that its actual conditions are now negative 10 kilojoules per mole? Let me do one more. What if I were to say this? Now its starting conditions are positive, or actual conditions are positive 10 kilojoules per mole. Where would I put my starting point in that case? So go ahead and pause it and predict where would I put my starting point, my Q value for those two quantities. Okay, so hopefully you have done that, and we can now look at this together. And just for clarity's sake, I'm going to go ahead and erase some things here, because this is getting pretty busy. I did not want to erase that. Okay, there we go. There we go. So when we look at this one, we have, again, negative value here. But very importantly, we have a different value, a different number, magnitude of number here. And we want to compare that to, of course, really negative 14 and negative 22. Of course, this is a smaller number than both of those, which means that under these conditions, we would be closer to equilibrium than both our previous actual conditions and our standard free energy change, which means that we should start somewhere maybe right around here. And we'll call this Q2. And we'll just put Q2 up here just to be clear. right? And in that case now, or even closer to equilibrium, it's still going to produce products to reach equilibrium, so it's still exergonic. But its potential energy is not nearly as great as it would be at standard free energy change, nor at our previous actual free energy change. Right, now, let's go one step further. Positive. All right, we have a positive actual free energy change. In this case, the reaction is going to produce reactants to reach equilibrium under these conditions, right? And so we would then put it actually over in this quadrant of the graph. And so I'll just pick a value here, and we'll just say it's something like this, and that would be Q3. And it's going to go in the opposite direction of what we've written it. And we would say it's non-spontaneous because the reaction is going in a direction that is counter to what we say the reaction will go in the cell. And it would actually have work to go in that direction. Okay? All right. Now, let's move over to our next graph. And let's look at one more scenario here. And in this case, we're going to look at our actual free energy change. We're going to notice that it's 0 kilojoules per mole. So we don't have a positive or a negative value here. We have a delta G that's 0. Now, what that means is this, that the free energy for this system at actual conditions is minimized, and the reaction would be actually at equilibrium. Right? Now, what that would indicate, because we are saying it's at equilibrium, we would say that the starting point for this reaction, let me find a color that is different than this, the starting point would be the same as the ending point. And we would say that this is Q for this reaction. And there would be then no driving force for the reaction to reach equilibrium. It would already be at equilibrium, and therefore delta G is 0. Right? Now, you can on your own, if you want, do this. We can give some more values here. We could say, all right, let's have an actual free energy change that's equal to -5 kilojoules per mole. Or we could have another one that's equal to positive 15 kilojoules per mole. And then finally, let's go one more, a delta G that is equal to positive 35 kilojoules per mole. Right? So pause it and find out where those would start. Where would I place Q for those? Right, now that you've done that, let's go ahead and look at these. Let's look at this one. Negative. That means that it's going to produce products to reach equilibrium. And that means that we'd have to put our Q value over in this quadrant of the graph to the left of KEQ. So I would put it somewhere right around here, and I'm going to call that Q2. Positive 15. We're back to a positive, okay? But 15 relative to the positive 29 here, that means that it's smaller value, okay? And we know that we started our reaction for that, positive 29, we started it here. So positive 15, because it's a smaller value, would be closer to equilibrium, but it would still be to the right of KEQ, so it would be somewhere right around here. And that would be Q3. And then finally, hopefully you're getting the hang of this, positive 35, this would be Q4. 35 being a larger number than 29, meaning that it's further from equilibrium, which means I need to put it in this quadrant of the graph. And so I'll put it somewhere right here. Now again, you can get exact numbers by using these equations and solving the equations for Q and KEQ. That would be a fine way to do this. Or you can do them as a relative positioning based off of these graphs. The whole concept that I'm trying to get across, though, here, when we look at the difference between standard free energy change and actual free energy change, is that they both end at the same point, KEQ, but they have different starting points, and therefore they have different potential energies. And that's going to be important because as we look at reactions in the cell, typically our actual conditions will differ from standard conditions. And we can use standard conditions to understand the ending point, the KEQ, but then we can use actual free energy change to understand the potential energy of that particular reaction within a cell, and whether work will have to be done to carry out that reaction, or whether that reaction can do work as it is carried out. Of course, the exergonic reactions can do work, and endergonic reactions have to have work done upon them. Right, I hope this has been helpful to you, and I will see you in class.